Here's another recap of what we've been doing with the third memo. Remember that from the last recap, we started out with y of t equals t squared, something that goes down, turns around, and goes back up. Here's the graph of that thing. And the velocity then looked like that it was, negative 0, positive. And we weren't sure exactly what that was. But we did some calculations. And we've got, for the t values, the y values are just the squares. And then these v values took a lot more work to get. For example, to get this number, v at t equals 2, what did we do? One way to do it, there's a few variations, but this is the basic idea. We look at 2, and we take the y value there, that's 4. Then we look really near 2, like 2.001, and we look at the y value there, 2.001 squared. You use a calculator for that, that's fine. And we look at that's the rise when we take the difference of those guys. On this graph, we're looking at the rise between 2 points. And we also look at the run. Well, that's just 2.001 minus 2. Well, that simplifies. It's just exactly this little scooch factor that we added. And we'll give official names to these guys. We're still playing with it right now. Well, the answer we get is very, very close to 4, 4.001. But is the answer 4.001, or is it really 4, or what else? What is it? Well, we looked at the trend, and you can look at 2.0001 or 2.quadruple-01. Do the same kinds of calculations, and you get numbers getting closer and closer to 4. That's very suggestive that the right answer is exactly 4. Because remember, the instantaneous velocity is really supposed to be the trend towards which these go. Similarly, we can get these guys. Well, look at what this function is. This is just a straight line function. Every time this goes up by 1, these guys go up by 2. And when this goes down by 1, these guys go down by 2. And in fact, it's just double this number. This number v is just double t. So in fact, we've come up with something very, very powerful. It's an incredible shortcut. There's a lot of work that was required to make these numbers. But the punchline is that the velocity, when y equals t squared, the velocity function is just 2t. We've now learned a new notation for that, and we'd say that the derivative of the function y of t equals t squared is this function v of t equals 2t. And we're going to get lots of notation for this kind of stuff. I'm not trying to obsess about that right now. Wow, that's really cool. And so it said, yeah, the slopes were negative 0, positive in about the simplest way possible. Now, what about y of t equals sine t? We looked at that, and we did the same process. So here's the y values, just the table of the y values. And then the v values, we did the same kind of thing. And here's the values people got. They got 1. And when t equals pi over 3, a lot of groups did this, and you got 1/2. Interesting. Pi over 2, you got 0, which makes a heck of a lot of sense. I think we've discussed that already. Pi over 2 is the height of the sine function. It's definitely got a horizontal tangent there. It's one of the few values you can just really read off with certainty. We got a minus 1 at pi, and then down to 3 pi over 2, we got a 0 again. And then we already had a conjecture as to what the slope function of this guy was. We were thinking that it was cosine t, and that's not what I want. I want math mode. Cosine t. So let's graph cosine t right underneath this thing. It seemed to match that when I can't get them both on the same picture. Okay. When this was going up, this was high. When this was flat, this was down to 0. These are just too big. Let me magnify for a second. There we go. And when this was flat, this was 0. When this was going down steeply, this was 0. It seemed like too good not to be true, right? Well, this confirmed, this table here confirms these are exactly the values of cosine. If we added another column in here and just put cosine t separately, not the slopes of the cosine t function, just plain the heights of the cosine t function. Remember, the slopes of this graph, of that graph, we're saying the slopes of sine t seem to give the heights of cosine t. Slopes of this graph are supposed to correspond to heights of this graph. So we're not going to actually do anything fancy with cosine. We're just going to evaluate it. Well, cosine of 0 is 1. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. And we get exactly the same numbers if we look down. That suggests that the derivative of sine is cosine. So we can say that now. The derivative of sine is cosine. Then everybody had some sort of guess as to the derivative of cosine. Okay, now we're considering this as the height function. Let me just put it down here. Okay, now we're considering this as the function that we're interested in, the heights, and now we're going to take the slopes of that guy. Ooh, okay, so this is, if this is the position, what are the velocity of this guy? It's going to be some kind of wave. Lots of people tend to guess sine. Is it sine t? And it's not quite, because that actually goes up when it should go down, and down when it should go up. But the simplest possible modification actually fixes it. Yeah, I might do a little more recap, but that's good.